Hey everybody, it's another road trip one. Let's go. Hello everyone and welcome to our latest location. Today we went on a very special road trip to Edison, New Jersey, to the Edison Township, which was originally Menlo Park. Menlo Park was originally the laboratory, was the location of the laboratory of one Thomas Edison, who was very, very important in the development of many technologies, including what we've been discussing, all about electronics. And he is most famous, of course, for the perfection of the light bulb. Many people think he invented the light bulb. He did not, in fact, invent it, but he made it practical. So practically, he was the one who brought it to us that we can use. Now, since then, of course, it's been improved on massively, but his was the first that could be used by everybody. And not only did he make the first light bulb, the first usable, practical, mass-producible light bulb, incandescent light bulb, he also made a power system that would go with it so you can then use your light bulb. Because if you have the light bulb but no electricity, what's the point, right? So he actually invented both the power system and the light bulb together. And then what he did is he wired it all up. He had everyone put out your lanterns and lamps and candles and what have you, turned it all on, and it was wildly spectacular that it all turned on. This was like the world heard that the incandescent light bulb is functional, it works, it's here. Rejoice, everybody. Edison has done it. And so when he did this, he got all kinds of contracts to build more of his power system. But here's the thing. For about 6 months, he had an employee. And this employee was Serbian. He came from an area which is now Croatia, but back then was part of the Austrian Empire. And his name was Nikola Tesla. He only worked for Edison. He wasn't even necessarily working with Edison, but he worked for him for about 6 months when he first came to the US, and then he quit. There was a variety of reasons why. Some say because Edison challenged him to build an effective motor. He built an effective motor, and Edison said, I'm going to give you $50,000, which in those days was like $12 million, if you do it. And he did it, and then he said, oh, you don't get our American humor, you're not from around here, I was kidding. And he didn't give him the bonus. Whatever the story may be, there was a whole bunch of different accounts. Edison did say it, Edison didn't say it, someone else said it. They definitely didn't have that kind of money lying about to give to this upstart new technician, engineer, brilliant though he may be. He was. Point being, Nikola Tesla quit. And Nikola Tesla was a brilliant, scary brilliant engineer and inventor. And he, along with his supporter, George Westinghouse, was the Westinghouse Power Company, he went directly in competition with Edison. But the basis of the competition was like this. Edison's light bulbs and all of his power system ran on something called direct current. Westinghouse and Tesla, their power system and all of their associated technology ran on something called alternating current, or AC. Edison had DC, Tesla had AC. And this sparked what came to be known as the Current War. So now we're going to talk about the Current War and who won and what happened in the various battles, the battle of the nerds, as it were, throughout. We're going to talk about that tomorrow. So today we're going to be talking all about alternating current, how it works, how you generate it, what it is. Let's get to it. So to explain how alternating current works, let's have a little demonstration of direct current. Now, before we show that, direct current is simply the usual way the current goes, the way we've been doing until now. There's a negative terminal, positive terminal, the electrons travel from the negative, go to the positive. Very simple, something like this. Now, in alternating current, the current alternates, meaning it switches from one side to another. First it's going one way, then it's going the other way, then it's going back and forth and back and forth and back and forth. This, of course, begs the question, why would you want your current to alternate? Let me explain. Alternating current happens because of how electricity is generated. We talked about generators. So we have a magnet and another magnet. And inside is a coil of wire that's spinning. Or in this case, me, that's spinning. And as the coil spins, the magnetic field is changing relative to the coil. It's not actually changing for us, it's just sitting there, but the coil is spinning. And so every time the coil makes a half turn, it's reversing the pull of the magnet. So first the magnet's pulling one way, then it's pulling the other way, and it's pulling one way, it's pulling the other way. The magnet's not moving, but the coil is moving, so the coil is experiencing the magnet pulling in a different direction. So now originally when this was made, when the original generator was created by Faraday, like we talked about a couple days ago, this had no real use. It was a curiosity, it was very cool, but it didn't really have any use to generate power to generate an alternating current, because what are you going to use it for? What's the point? Most of the time, back in those days when Faraday invented his invention, they were using it either for scientific purposes or for electroplating. We talked about that, how the ancients actually did this. You take a piece of cheap metal, you take a piece of expensive metal, you coat it, but you can't do that with alternating current. It doesn't work. For electroplating to work, you need the current flowing in one direction, which carries the little bits of metal to plate it. But if it keeps switching back and forth, you're going to end up with half coated and the other half's coated with it doesn't work. So when Edison designed his generators, what he did is he included a function inside that generator to stop the current from going back the other way. The coil would still flip, and so it should generate a current going back the other way also, but he devised a device that simply breaks the circuit when it's going the other direction, which is great. Doesn't get you as much power as if you left it on the entire time, but it does then create a single direction of current, which is very helpful, say, for his light bulb that he made. So he made all these generators, and he said, look what we've done. He said, look, well, we're so special. We've come up with this technology, and he went and he got a whole bunch of contracts to sell this. Before we continue with alternating current, we just need to point out something, is that nearly all of your appliances at home run on direct current. Meaning, let's say your laptop computer, it's plugged into the wall, right? Plug it into the wall, it's charging the battery. That doesn't work with an alternating current. If it alternated, then it would simply charge it and then discharge it, charge it and discharge it many, many times a second. So what your laptop actually needs to do, there's a little box from that cord that stops the alternation. It turns that alternating current you get out of your wall into a direct current that goes into your laptop. Let's say your lamp. You plug it into the wall. Inside that lamp base, there's a device that stops the alternating of the current and just allows you a single stream of current, a direct current. So that bears the question then, why are we doing this? Why are we alternating our current? Why don't we just make a direct current? Why are we causing extra complication back home for us when we're using the electricity? Why don't we just deal with it at the generator? So there is one massive, extremely important to life today would not be, you know, all the things we said pretty much in this class have been, life today would not be the same without it. So just that should be a given. Life today would be very different without this invention. And alternating current has an extreme benefit over direct current, and that is its ability to travel very, very far distances. So, what's the difference? I will explain that also. We talked about conductors, and when we talked about conductors, we had a term, resistance. It's futile. No, it's not futile. Resistance is what happens in a material that's not a superconductor, and it wastes electricity, it wastes power, it generates heat, it doesn't deliver all of the electricity to the other end. Now, nearly all materials have some resistance unless they're superconductors, like we just said. So, however, there is a way to reduce that resistance. So, we're gonna cut in a sequence with the highway right now. So now let's take a look at me from the highway. And on the highway, I was driving relatively quickly. I'm driving at the speed limit, but even that's what, 60 miles an hour? That's quite fast. 65, that's quite fast. Okay? But let's take a look at this other clip from the highway, and you see I'm driving much slower than that. You can't tell exactly how fast because you're with me on the dashboard, but I'm traveling 40, 30, something like that. So, to use these as a bit of an analogy, when electrons are traveling along a copper wire, let's say a copper wire, the amount of resistance that they make has nothing to do with how fast they're going and has everything to do with how many are lined up at one time. In other words, volts don't matter, amps matter. Okay? So, the more amps you have, the more resistance, and the more your power you're going to lose. The more volts you have and the fewer amps you have, the less resistance, and you can send your current very far. Let's say you were to take a massive amount, very, very high voltage electricity and use it in your home appliances are going to melt into a puddle on the floor, which is not useful to you or me or anyone else. Home appliances are not designed to take the stress of a massive amount of voltage, and there's a reason for that, is because to design them like that will be vastly impractical. So Edison's original light bulb had a relatively low voltage. Even today, most of our light bulbs have a relatively low voltage. Now, practically that means that for Edison, when he was using direct current, he could not make the current higher or lower or anything. He could just transmit it along his wires exactly as is, which means that if he has a power plant off, let's say, for random example, no bearing on what's actually going to happen, in Niagara Falls, he can't provide power to Passaic because along the way, all the power is going to get turned into heat along the wires and it's going to be useless. However, if you're using alternating current, you can send it from Niagara Falls to New York City, to Trenton, to Edison, where we are now, or to Passaic. How can you do that? The answer? Transformers.